Hello! So in today's video, we'll be talking about principal components analysis. We'll look at some examples of how this all works, what the math behind it is, and then how to apply principal components in R. So principal components is an example of unsupervised learning. So again, unsupervised learning just means that we don't have a right answer about our data. So we'd like to know or explore how these input variables are specifically related to each other rather than using them to make predictions on some output variable. Now, the kinds of questions that we ask when we're doing unsupervised learning, is there a way that we can combine our input features? Can we make interesting subcategories? Or can we make interesting groups of observations? Now remember, there's no right answer in this unsupervised learning process. So really, this is more like exploratory data analysis than anything else. We're no longer trying to make predictions. Now, broadly speaking, unsupervised learning falls into two major types of problems. The first are clustering problems. So in clustering, what we'd like to do is make a subgrouping or classification of observations. So maybe we have inputs that we'd like to classify as being measurements from beer, pizza, or hamburgers. Now with clustering, there's no target classification to compare to. So we're really just looking for some maybe natural groupings in the data set. The other type of unsupervised learning problem are dimensionality reduction problems. So here we might try to take a set of P input variables and reduce it to a much smaller set of M variables. We've actually done a little bit of dimensionality reduction already. We talked about using principal components in link with regression to build a regression model that had fewer inputs. Today, we'll talk about how that principal components procedure really works. So here's the notation. We're going to have N observations. We'll take measurements on P input features, and we'll call those inputs x1, x2, up through xp. When we do principal components, our goal is to find a low-dimension representation of the data that captures as much information as possible. When we're thinking about how much information we can capture, we're trying to explain the variability in the data set. For this set of features, the first principal component is the normalized linear combination of the features. So we'll take each of our input variables x, multiply them by some constant phi, get a new term or a new variable z1. That's our first principal component. We're going to choose these coefficients. We're going to choose the phis so that z1 has the largest possible variance. Now we can arbitrarily increase this variance just by increasing the size of these coefficients phis. So we add a normalization constraint. In essence, we want to have some upper bound on the size of these coefficients. Our normalization constraint is that the sum of the squared coefficients for this principal component must be equal to 1. Now, as you can probably tell from this description, the scale of the input features is going to matter as well. If we're limiting these coefficients to be less or to sum up in terms of their square to 1, we might want to limit or restrict the scale of those input features as well. So that vector of coefficients phi, we refer to that as the loading vector. Each individual coefficient, so phi I1 or phi 1i, phi 2i, these are the loadings. Another term for these are the rotations. That's the term that R uses in particular. So, given our data, how do we actually compute each of these principal components? So we'll make an assumption here, and I'm going to assume that each of the variables in x has been centered to have mean 0. So in other words, we're going to force all of the variables in x to have essentially the same units. We'll also scale each of them to have standard deviation 1. So essentially, we'll compute z-scores for each of our variables. Once we do that, the first principal component loading vector is then the solution to this equation or this set of equations. So we'd like to maximize the sum of these loading vectors, or the average of these. This j should be down in the subscript, subject to our constraint on the fees. Now it turns out that there's a really elegant way to solve for this in terms of matrices. So I'm going to let the data matrix X have sigma representing its covariance matrix. So sigma is the covariance between all of the variables. That sigma matrix has eigenvalues. We'll call those lambda 1, lambda 2, lambda p, all positive. So consider the linear combinations. We can write each of these principal components essentially just as some linear combination. A times x, we'll replace that with phi times x momentarily. In this setup, we have some properties. So the variance of any one of these linear combinations is the vector of coefficients, so A transpose times sigma times A. The covariance is A transpose for variable I times sigma times A for variable j. So this first principal component is going to be chosen such that this variance gets maximized. Our constraint in matrix or in vector terms looks like this. A transpose times A will equal 1. Here's another nice feature that we'd like to require for these principal components. We would like these linear combinations to be uncorrelated. So in other words, principal component 1 should not have a correlation with principal component 2. The way we do that is by placing a restriction on this covariance. Specifically, we're going to choose our solutions such that this covariance is equal to 0. Okay, so it turns out that if sigma, the covariance matrix, has the following eigenvalue-eigenvector pairs, so we'll use lambda to indicate the eigenvalues, e to indicate the eigenvectors, then each principal component turns out to just be the eigenvector times the data. So the first principal component uses the first eigenvector transposed. Second principal component uses the second eigenvector transposed, and so on. So these eigenvalues and eigenvectors are incredibly useful for calculating principal components. For each principal component, the variance of that component ends up being the eigenvalue. And it works out because those eigenvectors are perpendicular or orthogonal that this covariance is 0. So this is a really slick way to find independent linear combinations of variables. So some results from this setup. First, principal components are linearly independent. In other words, each component is independent of all others. So if you have a set of data where your input features are highly correlated, it might make sense to reduce that down to the principal component representation first. These eigenvalues then represent, again, the variance of the ith component. So what that means is that we can find out how much of the variance is explained by, say, the first q eigenvalues, by summing up those first q eigenvalues, and then dividing by the sum of all p eigenvalues. Now, eventually, these eigenvalues are going to get smaller and smaller and smaller, which means that this proportion of variance that's explained will effectively start to level off. These new principal components won't bring much to the table in terms of explaining the variability. So our goal will be to figure out, well, how much or how many principal components should we keep to retain enough variation in our data? So let's look at some examples. We'll start with the breast cancer data set from the ML Bench library. We've seen this data set before. It was something that researchers used to classify samples as either benign or malignant tumors. So we have variables representing the cell thickness, cell size, shape, etc. And then we actually have some known classes for this data. So here's some questions that we might want to answer. First, which variables in this data set are similar? Certainly there will be a correlation between, say, cell size and epithelial wall size. Could we summarize or could we measure that correlation and maybe combine those variables up into a single variable? And then secondly, are there different important components for benign versus malignant tumors? So maybe some components better explain variability for benign tumors versus malignant tumors. So we'll start by first forcing all of these variables to be numeric. Remember, in the original data set, R was storing these as factors. We'll remove class and ID since those don't really bring us much in terms of variation of the data. And then finally, we will limit ourselves to just the complete observations. Now, this is essential. Principal components analysis cannot work with missing data. We can't calculate that covariance matrix, nor can we calculate then the eigenvalues and the eigenvectors. So what that means is that if you have missing data, you'll need to either impute the observations or drop the missing data first. So we've seen principal components implemented as a pre-processing method in CARET, but we haven't actually seen it as an analysis method itself. It turns out that this is a purposeful choice. Other unsupervised methods are also not implemented in CARET. So CARET is designed for supervised learning, not unsupervised learning. Here's a good reason or a good way to think about this. Remember what CARET stands for. CARET provides methods or implementations in R for classification and regression training. In unsupervised learning, we don't have an output variable, so we can't actually train to make predictions on a testing data set. So what that means is that we'll no longer be working with that CARET framework. We'll be using base functions. So the base function for executing principal components is PRComp, and here's how this function works. It's pretty simple. First, you'll input your data set. So breast cancer 2 is the data set with NAs removed and with only the input features. I'm adding 2 new options in here. Centering is true. This sets all of the data sets, or all of the variables, to have center 0. Scale equals true, forces them all to have standard deviation or variance 1. I'll then save those results in the cancer_PCA object. I can use that summary function that's provided in R to take a look at these principal components. Now, there will always be as many principal components as there are input features. So we had 9 input variables. We've got 9 principal components. The first principal component, PC1, that explains 65% of the total variation in the data set. So we can make that one linear combination and really capture about 2/3 of the variation that we're actually seeing in our data set. The second principal component brings much less to the table. It only captures about 8.5% of the variation. Third principal component captures about 6%. As we increase, notice that this cumulative proportion, so the proportion of all variation that we are explaining, begins to start leveling off. So are we okay with maybe a loss of variation in the data and fewer features? Yeah, we might be. So let's see how this is all actually linked to those eigenvectors and eigenvalues. So sigma is my covariance matrix. Here I'll use the core function in R to calculate this. Now, kind of a misnomer here. This correlation function will, unless the data is scaled, actually produce the covariance matrix. So we've got this here. If we look at the eigenvalues, we have 5.9 for the first eigenvalue, 0.765 for the second eigenvalue. We also then have these eigenvectors. These eigenvalues actually represent the variation or the variance that's explained by each successive principal component. To relate that back to the standard deviation that's reported in the PCA output, remember that link or that relationship. Standard deviation is actually the square root of the variance. So if I take the square root of the eigenvalues, I get that standard deviation coming from each principal component. So then again, if we want to take each of these eigenvalues, divide them or scale them by the sum total of the eigenvalues, we get the proportion of variance that is explained by each principal component. Pretty cool. Now, how do we interpret these? The magnitude of these coefficients actually tells us how important a variable is in each principal component. So the larger the magnitude, either negative or positive, the more important that variable is. First, before we go into these, I want to show you, take a look at these numbers in the factor loadings or the rotations. They're exactly the same as the eigenvectors. So looking at the first principal component, all of these variables have about the same magnitude. All of them are contributing about the same. So it's really difficult to distinguish in that first principal component what variables are really making a difference. So if the first principal component can best be interpreted as just a little bit of everything, everything's important. The second principal component, though, has a more clear meaning. So in the second principal component, mitosis is the most important contributor, has the highest loading or the highest rotation. So mitosis is definitely important for explaining that second piece of variation. So are chromatin, bare nuclei. The rest of these are less important. The third principal component really looks like cell thickness is coming into play here. So cell thickness is important, maybe negatively related to marginal adhesion as well, and so on. So that's how we would work through interpreting each of these principal components. Sometimes there will be a clear differentiation, sometimes there won't be. So how many of these components should we actually retain? So as a rough rule of thumb, we should retain enough components to explain about 80 to 90% of the total variance. So we want to be able to explain enough of the variance, we're okay leaving those little ones at the end. One way or one tool that I like to use to help me interpret these is something called a scree plot, and I use more of a heuristic measurement. I look for where the scree plot levels off, so where we see the elbow. I'm going to use a library in R to help me out here called factoextra. This library contains a set of helper functions for doing factor analysis. Principal components is one type of factor analysis. So I will use a function called fviseig. So this is going to help me visualize the eigenvalues or the eigenvectors from this cancer PCA. This is actually what's going to create my scree plot. So we'll take a look at this. What the scree plot does is graph a bar for each of the dimensions or each of the principal components and allows us to actually see where this is starting to level off. That option here, add labels equals true, that's what provides the actual percentages along with it. So where this is starting to level off, right about here, I might keep maybe the first 3 or 4 principal components from this data set and throw out all the rest. Now, if we want to look at how the variables are related, we can create what's called a direction plot. So what this direction plot does is plot 2-dimensional vectors. The first dimension, or the horizontal dimension, is the first principal component. The vertical dimension is the second principal component. So what this shows you is how these variables come together in the first two components. So vectors that are strongly horizontal indicate variables that contribute strongly to the first principal component, but not really the second. Vectors that are strongly vertical indicate variables that contribute strongly to the second principal component, but not necessarily the first. And then vectors that are kind of in the middle are contributing to both. So it looks like that first principal component really contains about everything, and everything has a negative coefficient to it. The second principal component is really dominated by mitosis. That's the one that's the most vertical out of these vectors. You can also then color these. So if you want to distinguish them a little bit more, I like to color these variables based on the contribution. So this contribution here is a measure of importance. So how much each variable is contributing to each of these components. So it's kind of difficult to see in this first principal component, but cell shape has the most contribution to this first principal component. So it's got a nice light blue, whereas we've got kind of a lighter blue with mitosis, being that it's got the biggest contribution to the second. So the variables that are correlated, in other words, with the first and second principal components, these are the ones that are most important in explaining the variability. These have the highest contributions. So those contributions are actually a measure of how strongly correlated each of these input variables are to the first and second PCs. Variables that are close to the principal component will also have what's called a high squared cosine. So that's another way that we can represent these. Variables with a low cosine squared are not well represented, or you can think about it this way, they're not really well contained in those principal components. These measurements kind of go hand in hand. So if you look at the variables that are strong in terms of the contribution versus variables that are strong in terms of the squared cosine, you get very much the same pattern. So you can use either one. So what are some advantages of principal components? First, there is reduced dimensionality of this. We have a much simpler data set. You'll have to excuse me, I dropped my pointer. Second advantage, the principal components are independent. There's no correlation between these. So if you're working with a method that requires your input variables to be independent, principal components can really buy you that new relationship. One of the first major advantages here is interpretability. So sometimes the principal components have an understandable meaning, and sometimes they really don't. So let's look at this data again and see if we can tell if there's a difference in the principal components for benign versus malignant tumors. Now I'm going to set up these two data sets, one for the malignant tumors, one for the benign tumors. I'm going to use a different notation for dropping these NAs or removing those. I'm going to use tidyverse style notation, so let me walk you through this if it's been a while. We'll take the breast cancer data set. We'll filter out and only keep class malignant. We'll then select using a negative, actually removes these variables. So we'll remove ID and class, and then we'll drop the NAs. Same for benign. Creating that principal component for the malignant tumors, we can see something's changed. That first principal component doesn't explain as much as it did before. These next few principal components are each carrying a bit more of the variation. Looking at the scree plot, we're still not quite seeing that leveling off. Where to drop principal components is a little bit more difficult to tell. We don't really have a clear sort of leveling off point beyond this first principal component. Certainly we'd want to keep more than 30% of the variation. So how many to keep? I might say 4 to 5. We can also look at the important variables. So we're seeing a bit more distinction here. Variables that are important in the first PCA. Cell shape looks like is very important. It's difficult to tell what the second one is. If I had to guess, it looks like it might be cell thickness. So shape, thickness, nuclei also look like they're pretty important with that first principal component. Second principal component, cell thickness and bare nuclei. So we can kind of see that the important variables have changed. Same thing for benign tumors. We're seeing less variation explained with each principal component. So that's a little concerning. We also see different important variables with the benign tumors. So mitosis is very important on the second dimension for the benign tumors, whereas it wasn't as important for the malignant tumors. So that might give us a way to decide or to determine which variables we would look at from, say, a cell reading and use to help us determine whether a tumor is actually benign or malignant. Let's look at one more example with principal components. So the dataset college contains data for 777 colleges and universities featured in U.S. News and World Report. We have information like whether or not the school is private, number of applications, acceptance rate, actual enrollment rate, how many are in the top 10% of their class, top 25% of their class, and so on. So these are just some of the features that U.S. News and World Report uses to rank colleges and universities. As you might expect, there are some very strongly correlated variables in this data set. So acceptance rate is certainly correlated with the number of applications, as is enrollment. Number of undergrads correlated with all of these as well. Top 25% and top 10% class rankings are correlated. Expenditures are correlated with top as well. So we would love to, if we can, try to capture these correlations and reduce the dimensions of enrollment. So we will fit this model. Notice I've removed in this one variable from the front of this college data set. These are actually the names of the colleges and universities. So those have been removed. Of the 17 input variables, we could, looks like, get away with keeping maybe 5 to 6 principal components. So reducing this dimension pretty dramatically. These first two especially look like they are highly important for explaining the variation. The first principal component looks like it maybe includes things like the quality of the class. So we've got top 10%, top 25%, number of instructors with a terminal degree in most disciplines. This is a PhD, so you can see that those are going to be highly correlated. For the second component, that looks like it's taking proportion of undergrads, so personal rankings into this as well. Student-faculty ratio looks like it might actually be negatively related to top 25, top 10%. So maybe some universities with higher groups of high-performing high school students are those universities with higher student-faculty ratios, or maybe lower student-faculty ratios. Yes, it would be lower, so smaller class sizes are really attracting those students, for example. So that wraps up our introduction to principal components. You'll get a lot of practice with this sort of analysis on the homework assignment, and I'll see you in the next video. Have a good day.